So here we're going to look at what to do if you can't evaluate a limit by substitution or using algebra. And there's a nice rule that's going to allow us to evaluate limits whenever we get what are called indeterminate forms. So I asked this question here: what is the problem with plugging in 0 into this limit? Well, if you plug it in, you get 3 times 0 minus sine of 0 divided by 0, but that ends up just becoming 0 over 0, and this is called an indeterminate form. Now that doesn't mean that this limit has no answer or that the limit doesn't exist. It means we need to do more work. So incidentally, in this case, we could use algebra. I could write this as 3x over x minus sine of x over x, which is equal to 3 minus sine of x over x. And as it turns out, we know, using a little property of limits here, as it turns out we know what the limit as x goes to 0 of sine of x over x is, but probably only because you either saw a graphical representation or maybe somebody gave you a nice proof. But the point is, so that's 1. So this ends up being 2. So that wasn't so bad, but there are certain limits that you cannot evaluate using algebra, and you get this indeterminate form. So we're going to look at something called L'Hopital's rule, which allows us to evaluate limits that are in an indeterminate form. So L'Hopital's rule is going to allow us to evaluate limits that are in what are called indeterminate forms. So the word indeterminate literally means cannot be determined, and it's always important to remember that whenever you come across a form like this, it doesn't mean there's no answer. It actually means that almost anything could be the answer, including that there is no answer. But numerical values or infinity or any of those things could actually end up being the values of the limit. So L'Hopital's rule says that if you're looking at a limit such that the value of the functions f and g in this case equals 0 at x equals a, that would mean this, in this case, this is an indeterminate form there. And the derivatives at a for both functions exist, and the denominator doesn't end up being 0, then the limit of the ratio is equal to the ratio of the derivatives of those functions at x equals a. So in other words, you can figure out the value of the limit by comparing the derivatives at x equals a. So I think rather than do a proof of this, I'm going to do something a little more informal because I think it'll actually be a little bit more enlightening than the proof, which is kind of a bunch of symbols moving. So just to imagine that our functions up here, f and g, are graphed, and the curves bend, but at x equals a, they both equal 0. Now we know that if you zoom in close enough onto functions, they behave like lines. That's one of the underlying ideas in calculus. So let's let m with a little f, m sub f and m sub g be the slopes of f of x and g of x. Right, so let those two expressions be the slopes at the curves. The slopes of the curves, or more specifically the slopes of the tangent lines at x equals a. So then we can say that means that f prime of a equals m sub f, right? The derivative at x equals a is the slope at x equals a. And we can say that g prime of a is equal to the slope is equal to m sub g. So that means that if we take the limit as x goes to a of f of x divided by g of x. Now again, we can't plug a in because you get 0 over 0, but since we're interested in the values of this expression as x gets arbitrarily close to a, that means that we can treat f of x and g of x as the tangent lines that model them at those points. So what's the tangent line to f at x equals a? Well, the point a comma 0 is on this graph. So we can use point slope form to get an expression for a. So point slope form would be would look like this. M sub f divided by x minus a, right? I mean, it would be y equals that, y minus 0 equals that. And likewise for g, right? And so now you can see what's going to happen. Those go away, and we get the limit as x goes to a of the slope of f at x equals a and the slope of g at x equals a, but that's just f prime of a divided by g prime of a. So again, you can see that if you just compare the functions by comparing what their linearization or tangent line is at x equals a, you can see that the ratio of the slopes is the same as the ratio of the functions themselves at x equals a. So let's revisit that other problem and use L'Hopital's rule to evaluate it. So let's actually use L'Hopital's rule to evaluate this. Since we're getting 0 over 0 by plugging 0 in, we end up getting an indeterminate form. So we can use L'Hopital's rule, which says that this is equal to the derivative of the numerator divided by the derivative of the denominator evaluated at x equals 0 in this case. So this is 3 minus cosine of x divided by 1 evaluated at x equals 0, which equals 3 minus the cosine of 0 divided by 1, which is 3 minus 1, which is 2. And so you can see that L'Hopital's rule produced the same answer that we got when we used a little algebra. So we'll look at more examples of L'Hopital's rule in upcoming videos. Just remember that it only applies to indeterminate forms. You can't use it all over the place. I find a lot of students get carried away and use it all the time. Only indeterminate forms will require considering this technique.